We are now going to look at reflection of plane waves at normal incidence to a boundary. So we have two materials here. We'll call one material 1, the other one material 2. They can each have a conductivity, a permittivity, and a permeability. And we're going to put the boundary at z is equal to 0. So the xy plane is the boundary between the two materials. We'll have an incident wave, a reflected wave, and a transmitted wave. The incident wave is propagating in the plus z direction, so when the electric field is in the plus x direction, the magnetic field has to be in the plus y direction, so that E cross H, the power flow, is in the plus z direction. The reflected wave is traveling in the minus z direction, so when the electric field is in the plus x direction, the magnetic field has to be in the minus y direction, so that E cross H, the power flow, is pointing in the minus z direction. Finally, for the transmitted wave, which is propagating in the plus z direction, when the electric field intensity is in the plus x direction, the magnetic field intensity will be in the plus y direction. Here is the incident electric and magnetic field intensities using phasor representation, and we'll write the magnitude of the magnetic field intensity using the magnitude of the electric field intensity and the intrinsic impedance in material 1. Similarly, here is the representation for our reflected waves, and notice that the exponent here is positive to indicate the propagation is in the minus z direction. The minus sign here is to satisfy Poynting's vector for our reflected wave, which is propagating in the minus z direction. Finally, the representation for our transmitted electric and magnetic field intensities. At any location in material 1, the electric field intensity is going to be the sum of the electric field intensities from the incident and reflected waves at that point. And similarly, the magnetic field intensity at some location in material 1 will be the sum of the incident and reflected magnetic field intensities. In material 2 is just the transmitted wave, so the electric field intensity and magnetic field intensity will be that of the transmitted wave. We know at the boundary between two materials that the tangential electric field intensity is continuous and the tangential magnetic field intensity is continuous. Because our wave is at normal incidence, we only have tangential components for the electric and magnetic field intensities. I will designate the electric field intensity in material 1 at the boundary with the z value of 0 minus, and the electric field intensity in material 2 at the boundary with the z value of 0 plus. So here's the relationship between the incident, reflected, and transmitted electric field intensities at the boundary between the two materials. Similarly, here is the expression for the relationship between the incident, reflected, and transmitted magnetic field intensities at the boundary between the two materials. So here I'm just rewriting the relationship between the electric and magnetic field intensities at the boundary between the two materials. At z equals 0, we see the electric field intensity is just the amplitude of our electric field intensity, and at z equals 0, the magnetic field intensity is just the amplitude of the electric field intensity divided by the intrinsic impedance of material 1. Similarly, for the reflected wave, and at z equals 0, the transmitted electric field intensity is just the amplitude of the electric field intensity, and the transmitted magnetic field intensity at Z equals 0 is just the amplitude of the electric field intensity divided by the intrinsic impedance of material 2. So here we've made those substitutions. So we can solve for the amplitude of the reflected electric field intensity in terms of the incident electric field intensity and the amplitude of the transmitted electric field intensity in terms of the incident electric field intensity. This term here we're going to call the reflection coefficient and give it the symbol gamma, and this term here we're going to call the transmission coefficient and give it the symbol tau. Knowing the intrinsic impedances of the two materials, we can calculate the reflection and transmission coefficients. The reflection coefficient will tell us what fraction of the incident wave gets reflected, and the transmission coefficient will tell us what fraction of the incident wave gets transmitted. Next, we will look at some applications.